Good morning guys and welcome to the next part of the circles chapter. But before I move on to the next part, let me have a small recap of all the concepts or all the terms that we have studied so far. So when the chapter began, we learnt about a few terms like chords, segments and the pizza shaped sectors and arc, major arc and minor arc, which is part of the circumference. Then we learned about segments also. Then after that we learned about chords and the arc and how the angle is subtended by them in the center of the circle. They are equal for equal chords and equal for equal arcs, etc, etc. Then we moved on to a very basic concept wherein we learnt about the number of points we require to draw a circle, which is 3 points. And in order to prove that, we joined the 3 points using 2 chords, drew the perpendicular bisector, and finally ended up with a circumcircle and a circumtriangle. And I explained in the 2 sums how you can, basically keep a triangle inside a circle, in which all possibilities are there, especially when it is an isosceles triangle. And what should you do when you have an equilateral triangle as well. Then we learned a very nice theorem, which is perpendicular from the center of a circle to a chord bisects a chord. Then we proved equal chords are equidistant from the center, etc, etc, etc. Now the problem in geometry, or you can say a very, for a person who is very curious about geometry, a very interesting thing is that the theorems in geometry never seem to stop. There are so many theorems. So because there are so many theorems, you are kind of lucky that you have to learn only a few theorems. So the remaining part of the chapter, we need to learn mainly one theorem. The remaining 2 theorems are actually the outcomes of that particular theorem. Fine. After that, we learn about cyclic quadrilaterals. That is again based on one of these theorems. It's a very beautiful concept again. And so now we move on to the next theorem. And yes guys, if you have any doubt regarding the contents of this video, you know where to mail me. It is given below in the description box. So this is a circle, a random circle with a center O, okay? And P and Q are 2 points on the circumference of the circle, which is dividing the circumference into 2 arcs. So since, let me put P over here, I can see that this particular arc, okay, when I am naming a major arc, I will put one more alphabet over here, let it be A. PAQ is a major arc and you can see that PQ is a minor arc. Fine. Now, whenever you have 2 points along the circumference of a circle, you know that there are 2 types of angles in the sense, or 2 angles in 2 positions that we can draw. One is obviously the angle that these endpoints can form at the center of the circle. Another is the angle that it can form in the major arc of the circle. Okay. Of course, you can form angles in the minor arc also. Okay. Something like this. Right. Here also I can form. So, because these 2 points P and Q are dividing the circumference of the circle into major arc and minor arc, these 2 points PQ can form an angle at the center as well as in the major arc and in the minor arc of the circle. Our following theorem, which we are going to look at, is basically based on these angles. The angle that 2 points or 2 points which define an arc form in the circumference of the circle and in the center of the circle. What is the relation between both of these? Okay. Now let us draw a proper diagram and have a look at the theorem. We have a circle with a center O, and P and Q are 2 points that has divided the circumference into 2 arcs. PAQ is a major arc and PQ is a minor arc. So you can say that I have 2 arc PAQ and I have a minor arc PQ. Now, if I have taken a point A over here and I am planning to make an angle over here using these 2 points. So I draw 2 straight lines that will intersect at the point O, giving me an angle. So now I have got 2 angles, an angle over here and an angle over here. Okay. Now, PAQ is the angle subtended by which arc? I have got 2 arcs over here. I have got the major arc PAQ and I have got the minor arc PQ. Now, angle PAQ is an angle that is subtended at the circumference or the arc of the circle by the minor arc PQ. So, let us say we are talking about an ice cream cone. Okay. This is our ice cream cone. Ice cream cone with a different flavor at the base. Okay. We need to show that this particular angle is twice this particular angle. Your ice cream cone can also end up like this. It doesn't matter, which means that this particular angle can be anywhere on this arc. Okay, whatever I am going to tell you is gonna be applicable to any point on this arc on the side of PQ. Okay, now let us move on to the proof. I hope you have understood what exactly am I going to relate. I am going to relate the arc, the angle subtended by the minor arc PQ on the circumference of the circle and the center of the circle, which looks like an ice cream cone if I were to eliminate this part. Okay, now let us see what is the relationship that we can derive. Now have a look at this diagram. You have a circle with center O. P and Q are 2 points which has divided the circle again into major and minor arc. We are going to talk about the angle that is subtended by the minor arc PQ on the circumference of the circle, which is angle PAQ. We have an angle at the center also. Okay, I have joined the points A and O, which is the center of the circle, and the point A which I have taken on the circumference of the circle. Now, I cannot use congruence to prove anything in this. What is the reason? The reason is because the two triangles which you can see over here, they are not congruent at all. Depending upon the position of A, as A keeps moving from here to here, one line becomes longer than the other. Correct? So, depending upon the relative position of A, the relative length of this particular chord and this particular chord will keep on changing. So, there is no question of me taking congruence at all. Fine. So, how do I prove it? I know that this is the exterior angle for this triangle. So, if this is theta, I am just calling it as theta. So, this is equal to angle QA or angle OAQ plus angle OQA. The reason being exterior angle is equal to sum of the opposite interior angles. And suppose this is theta 1. What can you say about theta 2? I can say that theta 2 is equal to OAP plus angle OPA. Okay. Now, what can you say about this angle and this angle? I can say that these two angles are equal because they are the base angles of an isosceles triangle. This side and this side are equal. This side and this side are equal. They are the radius of the same circle. So, I can say that the base angles are equal. Okay. So, I can say that angle OAQ is also equal to angle OQA. Fine. So, my theta 1 will be equal to 2 angle OAQ. Similarly, my angle theta 2 will be equal to 2 angle OAP. What is my total angle equal to? Theta 1 plus theta 2, which is equal to twice of angle OAQ plus angle OAP. What is OAQ plus OAQ plus OAP equal to? That is twice angle PAQ. So, I have proved that the angle subtended by the arc at the center is twice the angle subtended by the same arc at the circumference of the circle. Fine. Now, this proof we have done taking PQ to be a minor arc. Let us consider the case when PQ becomes a semicircle. Semicircle means this P and Q are exactly on both sides of the center, and if we draw a chord, that chord has to pass through the center joining P and Q. Okay guys, now have a look at this diagram wherein I have taken P and Q to be 2 points exactly on the opposite side of the center, dividing the circumference into 2 semicircles. Okay. Now, the diagram is more or less the same except the positions of P and Q have changed. The proof also will remain the same. This angle is equal to this plus this. This angle is equal to this plus this. But since these are all equal, this become an isosceles triangle, each become an isosceles triangle, as a result of which this angle and this angle are equal, this angle and this angle are equal. So, just apply the manipulation and you will get the same theorem. Okay. Now, when I'm doing this theorem, what is one point that sticks out when I'm doing this particular theorem? You already know that if I am joining P, O and Q, it will become a straight line, right? So, at any point on the straight line, if you're going to measure the angle, what is it equal to? This angle is anyway going to be equal to 180 degree. And obviously, this angle is also going to become 180 degrees. So, when we are talking about the angle, we are talking about this angle, right? Angle subtended at the center of the chord. See, in this diagram, this was our angle subtended at the center. Now, this point has stretched out to here. Again, angle subtended at the center is again this angle. So, this is also 180. So, according to our original theorem, the angle subtended at the center is twice the angle subtended at the circumference. Correct? So, if angle subtended at the center is 180, what can you say about this angle? It is a 90 degree. So, this is the first result that we are getting from this particular theorem. The angle subtended in a semicircle is a 90 degree, or angle in a semicircle is a right angle. A very nice way of putting the statement. So, this is the first result that you are getting from this theorem. Very important one, applicable in many sums. Please remember it, angle in a semicircle is always a right angle, and this is how you prove it. Okay. Now, we have considered PQ being a minor arc, PQ being a semicircle or a semicircular arc. Now, we need to see what happens when PQ is a major arc. Let us talk about the angles when PQ is a major arc. Okay. So, you have a circle, you have the center of the circle, and initially PQ was here. Then PQ moved here. Now, let it move a little more upwards, creating a major arc over here and a minor arc here. Okay. I am taking a point on the remaining part or the circumference of the circle to be subtended by PQ. And I join PQ to the center. Okay. Now, the angle subtended at the arc is this. No doubt about it. What can I say about the angle that is subtended by the center of the circle? Now, looking at it, you can feel that this is our angle. But remember our original diagram? This was PQ. It didn't matter when PQ moved till here. This was our angle again. Now, why would it change just because P and Q has decided to change its positions? It doesn't matter. So, again, this will be our angle. Now, this is the angle that we are going to talk about. Correct? What is this angle called? Can I call it as angle POQ? Our normal thought process is our angle POQ something like this. Not something like this. So, what do you call this? We call it as the reflex angle. Okay? In this particular case, when P and Q has changed positions in order to create a major arc, we call the angle formed at the center as a reflex angle POQ. Proof is again the same. Join A and O. When you join, you know that this particular part is equal to this plus this. This particular part is equal to this plus this. Now, isosceles triangles, this angle and this angle are equal. This angle and this angle are equal. Each part is twice of this part and this part is twice of this part. Add them both, you get the same. The only thing that you need to take care is that we are talking about the reflex angle POQ. Okay, when the arc becomes a major arc, we are not talking about the normal angle POQ. Is something that should stay inside your head. Fine. Now, if you have a circle and you are taking two random points P and Q, you are joining this by a chord. You know that P and Q are 2 points that creates a major arc and a minor arc. If I am joining P and Q by chord, what do you get? You get a major segment and a minor segment. Correct? So, this part is our major segment and here we have our minor segment. If what can you say about angle PAQ and angle POQ? I know that angle POQ is twice angle PAQ. What can I say about this? Angle POQ is also equal to twice angle PBQ. Same proof. Any angles that we take in this particular part or in this particular segment, all of those angles are equal to half of the angle subtended at the center by the same chord. So, can I make it into a theorem? I can make it into a theorem saying that the angles in the same segment of a circle are equal. This was my segment, this was my another segment. So, any angle that I take, all these angles are going to be equal to half of. So, this angle is equal to half of POQ. This angle is half of POQ. This, everything is going to be half of POQ. So, it gives me the result. Angles in the same segment of a circle are equal. Okay. Now, we are going to do a few sums based on these few theorems, based on this, exactly actually only one theorem plus the two results of the theorem, and see how easy it is to apply these theorems. Now have a look at these two diagrams. The first one, we need to find the measure of angle AOC, which is this angle. Okay, O is given as the center of the circle and two angles are marked. Now let us start with this diagram first. So here you can see that, what can I say about angle BOC? Angle BOC is twice angle ABC, right? Now if we are joining B and O, what can I say about these two triangles? According to, we have done the proof also, we know that both of them are isosceles triangles, so the base angles are equal. So if this angle is 30, this is also 30. If this angle is 40, this is also 40. So what is angle B over here? Angle B is 70. So what can you say about this angle? It is twice that of angle 70, which is 140. Direct application of the theorem, a very simple sum. So please try out more sums like this, because there are so many ways in which this sum can be asked. In the second sum, angle BAC is given to be 30 degrees. O is the center of the circle. We need to show that BC is equal to the radius of the circle. Okay. Again, a very simple and a very direct application of the previous theorem. If this angle is 30, what can you say about this angle? This angle is 60. O is the center of the circle, meaning OB and OC are radii of the circle. So this angle and this angle are equal because this is an isosceles triangle. So this is 60 means the remaining angle makes a 120. Both of them are equal, 60, 60. So what kind of a triangle does this become? It becomes an equilateral triangle whose three sides are equal. So BC is also equal to OB is equal to OC, which becomes the radius of the circle. Okay. Now these are all very simple sums, and I think most of this kind of sums we can do. Now let us move on to a slightly tougher sum wherein they ask you to prove some, some chords are equal to this, some arc are equal to this, which are without giving any measurement. So it becomes a little more complicated. So let us see how to do them. In the second sum, angle BAC is given to be 30 degrees. O is the center of the circle. We need to show that BC is equal to the radius of the circle. Okay. Again, a very simple and a very direct application of the previous theorem. If this angle is 30, what can you say about this angle? This angle is 60. O is the center of the circle, meaning OB and OC are radii of the circle. So this angle and this angle are equal because this is an isosceles triangle. So this is 60 means the remaining angle makes a 120. Both of them are equal, 60, 60. So what kind of a triangle does this become? It becomes an equilateral triangle whose three sides are equal. So BC is also equal to OB is equal to OC, which becomes the radius of the circle. Okay. Now these are all very simple sums, and I think most of this kind of sums we can do. Now let us move on to a slightly tougher sum wherein they ask you to prove some, some chords are equal to this, some arc are equal to this, which are without giving any measurement. So it becomes a little more complicated. So let us see how to do them. Now look at this diagram. Here P is given to be the center of the circle, and you need to prove that angle XPZ is equal to twice angle xzy plus yxz. Okay, fine. Now, what they basically ask you is to prove that this particular angle is twice that of this angle and this angle. Okay. Now, sometimes when you get questions, when you are a really brilliant student, it is very easy for you to immediately gauge the steps or the concept that is given in the question. Now, if it is a very often asked question, or if it's a question from the NCERT, or a very common question being discussed from the reference books in your class, or you have studied, it very easily comes to you. You can immediately start writing the steps. Sometimes you get diagrams which you have not seen before, because it will be a diagram that is based on the concept that you have studied. But then that particular diagram, you will take a few minutes to understand what you need to apply and how to prove a particular sum. When you start with that, the first thing I always tell my students is write down all the facts that you have in your hand. All the facts, maybe it is relevant to the sum, maybe it is not relevant to the sum. Especially in geometry, write down all the facts that you are having and take out the facts and apply it as and when you feel whichever facts are required in order to solve that particular sum. So let me follow the second method, assuming that I am a very normal student who is looking at the sum for the first time. So let me write down all the facts. I know P is a center, so I know PZ is equal to PX is equal to PY. They are all radius of the same circle. When that is the case, I know that this becomes an isosceles triangle PZY and PXY. They are both isosceles triangles. Correct? In addition to the two sides, the base angles are also equal. So this complete angle and this complete angle, this is equal to this one. I didn't make it very clear. So I can say that this angle is equal to this and this complete angle is equal to this. Two isosceles triangles. Now, I personally prefer to name my angles by using theta or x or y or similar variables. If you are more comfortable with using, this kind of names, angle ABC, angle XYZ, please proceed. Because I am finding it difficult to, address the angles in this way, I am going to rename the angles. So, I also know that PZ is equal to PX. So, this particular angle, which is XPZ, is an isosceles triangle. So, if this angle is theta, this angle is also theta. Okay. Now, this angle is theta 1 and this angle is theta 2. This entire angle is theta plus theta 1, that is equal to this angle. This entire angle is theta plus theta 2, so this is also equal to theta 2. Now, I have all the data that I need. Now, I will think about the theorems that I can actually apply in this particular sum and then proceed with the sum. Now, here you can see that X, Z are 2 points on the circumference of the circle and it is subtending an angle over here. Correct? Plus, it is connected to the center also. Right now, we studied a theorem wherein we had 2 arcs and this was our first proof. Then these arcs changed shape and became semicircle like this. Okay. And what happened after that? The arc became a major arc PQ and it became like this. Our diagram is somewhat similar. So we know that there is a connection between this angle and this angle, which is a reflex angle. Okay. So my reflex angle XPZ is equal to twice angle XYZ, which is twice angle now reflex angle XPZ is actually 360 minus angle XPZ. That is our basic definition of a reflex angle. So this is equal to 2 angle XYZ. Okay. Now our angle XYZ is an angle of a triangle YXZ. So angle XYZ is also equal to 2 into 180 minus theta 1 plus theta 2. These are the other two angles. This is equal to 360 minus 2 into theta 1 plus theta 2. Now 360 and 360 gets cancelled and negative sign get cancelled. I am getting angle XPZ is equal to 2 into theta 1 plus theta 2, which is our angle YXZ and YZX. So we have proved it. So you can see that there was no need for me to take this particular isosceles triangle at all and name the base angles as theta. But you know, when you start doing a sum, I have done that in order to make you understand that when you are getting a sum, write down all the facts that you know. If you are not familiar with the figure, some of them might come useful, some of them you might not actually need it. But then you can actually make use of the facts that you are using or writing down in order to proceed with the sum. So you get a clarity on the sum that you are looking at also. Now you have done the sum in this particular way by taking the reflex angle and by using the theorem. Let us look at another way in which we can do this particular sum. So now let us see how we can do this particular sum in a different way. You just learned the theorem that if there is a chord or if there are 2 points over here, the angle at the center is twice the angle at the arc of the circle. It doesn't matter whether it is a minor or a major arc over here, minor or a major chord over there, whatever. Now, suppose this is a chord. This is the center of the circle. Okay. This chord is obtaining an angle here at the circumference. So let us okay, like this. You know that this angle is twice of this particular angle. Okay. Now this point is moving and coming over here. This is the angle at the arc now. So this angle is twice of this angle also. Correct? Now look at this particular diagram. XY is a chord. Okay. And this angle is the angle subtended by the arc or by the chord XY at the center. Now this chord XY also has an angle over here which goes like this. So if this angle is theta, what can I say about this angle? This angle is 2 theta. Okay. Now YZ is a chord. YZ is obtaining an angle at the center plus an angle at the circumference. So if this angle is theta 1, this angle is 2 theta 1. So my angle XPZ now became 2 into theta plus theta 1. Okay. Which is actually twice of this angle plus this angle. So here I have not used the reflex angle property, nor I have used the angle sum property of a triangle, nothing. I have just used the theorem that we have learned. We have a chord XY over here. This XY is obtaining an angle at the center plus an angle at the circumference. The angle at the circumference is theta, so this is 2 theta. Similarly, YZ is a chord that obtains an angle of theta 1 at the circumference. So it is obtaining an angle 2 theta 1 at the center. So this complete angle XPZ is equal to 2 into this angle plus this angle. So we have proved the sum. Prove that a circle drawn with any side of a rhombus is the diameter passes through the point of intersection of the diagonal. So we have a rhombus. Halfway or a part of the rhombus is inside the circle. The circle is also passing through the intersection of the diagonals of the rhombus is what we need to prove. So since it is given to be a particular shape, a rhombus, not just a random quadrilateral, the properties of rhombus, let us revise it or go through it once more. All sides of the rhombus are equal, but it is not a square because the angles are not 90 degree. The diagonals of a rhombus, they are not equal, but they intersect each other at 90 degrees. So far we know. So now let us draw the diagram. Okay, so I have drawn the diagram. Yeah, I know it is a very, very weird diagram, but this is our circle. O is the center of the circle and AB is the side of the rhombus. So AB, BD, CD and AC all are equal to each other, and BC and AD are the diagonals of the rhombus meeting at the point E and the circle is passing through it. That is what we need to prove. Okay, you know that angle AEB or this particular angle each is equal to 90 degree. AB is a diameter of the rhombus. AB is a side of the rhombus which is a diameter. Okay. Now this AB is having an angle of 90 degree over here, which is AEB. Angle AEB is equal to 90 degree. You know that angle in a semicircle is always a right angle. So you can say that the circle actually passes through the point of intersection of the diagonals of the rhombus. So you can say that it was a very simple sum, just the application of two concepts, the intersection of the diagonals of the rhombus and that the angle in a semicircle is a right angle. Okay. In the figure, AB is a diameter of the circle. Series a chord, measure equal to radius. AC and BD meet at E. You have to prove AEB is equal to 60 degree. So the diagram is already given to you. You need to prove this angle is 60 degree. Okay. So O is the center of the circle. Fine. So you know that OA, OB and CD are equal. Okay. Now, if I am joining OC, I'll get a triangle over here and so I will get is equal to OC is equal to OD. All of them are radii of the circle and CD is already given to be equal. So this side and this side are equal. So I have an equilateral triangle over here. So each angle will measure 60 degree. Okay. Now CD is a chord that subtends an angle of 60 degree at the center. So let us find out a point on the circumference where CD is subtending an angle. So CD, if I join this, I can say that this chord CD subtends an angle of 60 over here and at the same time it is subtending an angle 30 degree which is half of the 60 at the circumference of the circle. Okay. Now I have a triangle BCE out of which I know an angle 30 degree. The second angle is E, but I don't know this angle. Okay. I know that AB is subtending an angle at the circumference. That angle is 90 degree because AB is a diameter. Okay. So I know that ACB is a 90 degree angle because it is angle in a semicircle. So the remaining angle which is BCE will be 180 minus 90 which is equal to a 90. This is also 90 degree angle. So in the triangle I have got this is 30, this is 90. The remaining angle has to be 60 degree. Okay. So you need to make a few constructions over here of OC, OD and BC. This is the most important construction so that you get a 30 degree over here. Fine. So this, though it was direct application, the diagram we needed to make a small manipulation. We need to construct this CB over here. Find the measure of angle PQB. O is given as the center of the circle. This is our next sum. This is what we need to find. Okay. This is 42. Since O is the center, I can say that AB and PQ are diameters. So AB subtends an angle here that has to be 90 degree. Similarly, PQ has an angle over here which is again 90 degree. So, okay. Now this is 90 and this is 42. So this is 180 minus 90 plus 42 which will give me 48. Okay. Now, if this is a chord of the circle, this becomes angles in the same segment of the circle. So I can say that PAB and PQB are angles in the same segment. So if this is 48 degree, this also has to be 48 degree. Okay, so it is pretty easy. Just you need to apply angles in the same segment theorem on this. So we have found out this particular angle. Okay, two circles intersect at A and B. AC and AD are the diameters. Prove that CBD are collinear. Okay, so Before I start doing this particular sum, I just want to ask you, where have you come across the term collinear in this particular chapter? So in one of the videos or one of the previous lessons that we did in this particular chapter, I had mentioned the word collinear and where collinear points are applicable in the case of circles. I want you to think about where we have actually gone through that particular word and where we actually used it. Okay. See, when you study a chapter and suddenly when you're learning something and you happen to remember a particular word or a particular theorem, I want you to take 5 minutes of your time in between and think about where you have learned that particular concept and try to actually write it down in a paper and see whether you actually remember it or not. You can even do it inside your head, but then if it is too much for you, please do it in a piece of paper and see whether you are actually able to retain what you have studied. Okay, this actually helps when you are learning mathematics, because see, as and when you move from one theorem to the other, it is always a possibility. It always happens that you forget the previous theorem and how to apply it. When you do like this, you keep in touch with what you have studied previously, and so that you don't find it very tedious when you go back for revision. Fine. Now let us get on with this particular sum. Two circles intersect at A and B. AC and AD are the diameters. Prove that CBD are collinear. So you have two circles having centers over here. This is intersecting at A and this is intersecting at B. Now, AC and AD. So, collinear points are lie in the same line. So, if C, B and D has to lie in the same line, this angle has to be 180 degree, correct? Now, AD is a diameter. So, let me join this, A and B. I get two triangles, ACB and ADB. Now AD is a diameter. I know that angle in a semicircle is a right angle, or the angle subtended by the diameter at the circumference is 90 degree. So this angle is 90. Similarly, for the diameter AC, this angle is 90. So the sum of the angles is a 180 degree. So I can say that angle CBD is a straight line because the angle subtended at the point B is a 180 degree. So if you are having any doubts regarding the contents, please mail me. I hope you will be able to proceed with the sums that you are doing in the NCERT as well as in the reference book, and any doubt that you will be having, please feel free to mail me at the mail ID given below in the description box.